conveyor system. The objective is to design and simulate a DC motor control system for a conveyor belt using Simulink and Simscape. The main goal is to maintain a constant conveyor speed even when a sudden load disturbance occurs. In this project, we compare open-loop control, meaning without a controller, and closed-loop control using a PID controller. We also analyze the motor current during startup and steady-state operation. So here is our closed-loop control system for the conveyor belt DC motor. We are using a DC motor from Simscape connected to a mechanical load that represents the conveyor system. The motor speed is controlled using a PID controller in the feedback loop. The target speed is set to 150 radians by seconds. I will now run the simulation for 20 seconds and we will see the scope. So we can see that at 5 seconds there is a disturbance load, which is represented by the load here, the step block. And then at 7 seconds it regained the target as asked. So it simulates a sudden increase in load similar to placing a heavy object onto the conveyor belt. Okay, so I can stop it. Then here we are showing the Simscape solver configuration block used for the physical system. The model used a time-based equation formulation with derivative replacement for numerical stability. We kept the default automatic settings because the system solved correctly without convergence problem. We also enable connection filtering, like this, to improve stability between physical components. Since the disturbance occurs suddenly at 5 seconds, proper solver configuration and zero crossing handling are important for accurate transient response simulation because zero crossing detections allow Simulink to detect sudden changes or discontinuities precisely in time, and variable step solver automatically adjusts the simulation step size. So in our system, this happens when the disturbance torque is applied at 5 seconds. That's it.
Hi, my name is Fatin Amira. Next, I will demonstrate how the PID controller helps the conveyor system recover after a disturbance is applied. So I will open the set point versus actual speed scope graph. So in this graph, we can see they have two different color of lines, which is the yellow line is represents the set point, which is fixed at 150 radian per second, while the blue line represents the actual motor speed. As you can see, at the start of simulations, the motor accelerates from rest and quickly reach the target speed of 150 radian per second. We can observe a small overshoot before the speed stabilizes near the set point. This shows that the controller is able to achieve the desired speed quickly while maintaining good stability. At t equals 5 seconds, a disturbance torque is applied to simulate an additional load on the conveyor belt. As shown in the graph, the actual motor speed drops significantly because the motor suddenly requires more torque to drive the heavier load. The speed decreases to approximately 80 radians per second, creating a large error between the set point and the actual speed. However, because the system uses a PID controller, the speed error is detected immediately. Our final PID tuning values are proportional equals 20, integral equals 40, and derivative equals 2. The proportional gain provides a strong corrective action. The integral gain eliminates the remaining error, and the derivative gains helps reduce oscillation during recovery. As a result, the controller automatically increases the motor voltage and generates additional torque to compensate for the disturbance. We can clearly see that the speed begins recovering immediately after the disturbance occurred. Based on the graph, the speed returns to the target value of 150 per second at approximately 6.8 seconds. Since the disturbance was applied at 5 seconds, the recovery time is approximately 1.8 seconds. This result successfully meets our project requirement of recovering within less than 2 seconds after a disturbance. After recovery, the speed remained close to the set point with only minimal overshoot and stable operation. This demonstrates that the PID controller provides effective disturbance rejection and maintains consistent conveyor speed under changing load conditions. Therefore, the closed loop PID system performs significantly better than the open loop system. So next is efficiency and current analysis. And now I will show you the scope graph for current work. I will analyze the motor current response to evaluate the performance of the system under different operating conditions. If you can see, at the beginning of the simulation, the motor current is relatively high because the motor requires additional energy to accelerate from rest. Once the motor reaches normal operating speed, the current decreases and stabilizes at approximately 250 ampere. This indicates that the conveyor is operating under light load condition and requires less current to maintain the target speed. At t equals 5 seconds, the disturbance torque is applied, increasing the load on the conveyor system. As a result, the PID control commands the motor to generate additional torque in order to maintain the desired speed. This causes the motor current to increase significantly to approximately 1000 amperes. The increase in current represents the additional effort required by the motor to overcome the disturbance and restore the conveyor speed. After the recovery process is completed, the current settles at a higher steady state value. This is expected because the motor must continuously provide additional torque to carry the added load while maintaining the target speed of 150 radians per second. Therefore, the current analysis confirms that the controller responds correctly and supplies sufficient power to maintain stable conveyor operation under varying load conditions. So, to conclude, the PID control conveyor system successfully maintained the target speed of 150 radians per second and recovered from the disturbance within approximately 1.8 seconds. The current analysis also confirmed that that additional power was supplied when required to overcome the increased load. Overall, the PID controller significantly improved the stability, disturbance recovery capability, and performance of the conveyor system, successfully achieving all project objectives. That's all from me, and thank you.